Hello, students. Welcome to a new lecture, this time on the topic of regularization. And yes, I will struggle a little bit to pronounce this word, so apologies in advance. Um, Now, this is in the module 5, in the same module as the one covering cross-validation, but have in your mind that this is a new topic. This is a new modeling approach. Um, Now, to fine-tune it, this new modeling approach, we will need cross-validation. So it kind of makes sense that we put it in the same module, but yes, have in mind that now we're doing something different, a new type of model, if you want. So here, first in this section, regularization, we're going to discuss overall what is this method, a bit, theoretically, I suppose. But then we present plenty of examples. In this section, regularization plots, we'll have basically visualization where we're not going to insist on the actual implementation in R. We just want to illustrate the concepts. But then in the next section, we're going to use real data sets to do examples and focusing on the actual R commands. And lastly, we have a short section to revisit the intuition, because here, the first time you encounter this concept of regularization, you might not really understand why it makes sense. I'll try to explain it throughout, but the intuition of why it makes sense might take a bit of time to assimilate, right? So this is why we're going to try to revisit the intuition towards the end. But first things first, now let's present what is this method. And we start with this motivation. So here we make the distinction between tall data on the left, which is the situation we've encountered before or so far. You have more observations than predictors. So we distinguish that to the situation of what is called wide data, which is the opposite. You have more predictor variables in your data set than observations. Said otherwise, your data set, you have more columns than you have rows, because rows represent different observations and columns represent different predictors. And this is a problem for our, let's say, traditional linear methods, either linear regression or GLM more broadly. Traditional linear methods are fine in the first situation, but cannot deal with wide data sets. So they can fit data only when the number of observations is larger than the number of predictors. So those methods just break in the case of wide data, but our new regularization methods will work even on wide data, which is at least part of the motivation to present those methods. Okay, just an example in R to show you that you're going to have trouble in R if you try linear regression on wide data. So here, this will be the same data set as we've used in the cross-validation, the so-called glass door data set, where we had essentially the satisfaction of people working at universities in the UK. Now it's a relatively large data set, but here for the illustration, we're just going to keep the first three rows. So we just keep three observations, but then we have more predictors than, more columns than rows. If you try that, if you fit your linear regression the way you would usually do, R will actually give you outputs, but you see, we have problems. You can fit, if you have n observations, you can fit up to n parameters. So here you have, remember, we have three rows here in this modified data set, three rows. So yes, you're gonna be able to find an intercept. You're gonna be able to find the first predictor, the first beta, and the second beta, and that's it. For the rest, R cannot fit anything. And so here, this is more or less useless. Okay, so now we get to the idea of regularization, and frankly, it has several names, right? So here it says shrinkage methods. So yes, shrinkage and regularization, at least for our purposes, will be the same thing. Now you might first think, okay, well, maybe we could have just done our regular linear regression using subset selection, meaning, okay, I cannot use all predictors, but maybe I can just use a couple, and then I'll be able to fit my model. So I just pick one or two predictors, and then I'm able to fit everything. That is theoretically possible, but then it does have a big issue, which is that if you have lots of predictors, well, which one should you select? So imagine you have hundreds of predictors, and you want to select, I don't know, a couple of them or a few dozens of them. Well, there's so many choices to make. So you could do it in theory, but then you have thousands and thousands or millions of models to fit, and it might not actually be feasible in practice. So the alternative here is, again, what we're going to call uh, shrinkage methods or regularization methods. Now, in a word, what we do is we shrink the beta coefficients. The coefficients of the predictors, we're going to make them, in some sense, artificially smaller as opposed to what they would be under just linear regression. And so here we're going to see two methods, and those are the main methods, again, of regularization, the ridge regression, and this will push the betas towards zero, but the betas will not be exactly zero. So it's going to shrink them, make them smaller, but they can be very, very small, like 0.00 something, but they're not going to theoretically be exactly zero. As opposed to that, the second method that we're going to cover is the lasso regression, which similarly is going to push the betas towards zero, so it's going to shrink them. And here you can actually theoretically get betas that are exactly zero. So in some sense, you're completely excluding some predictors, while in the ridge regression, you keep all the betas, you keep all the predictors, but some of their coefficients will be very, very small. And yeah, okay, and you also have the elastic net. We're not going to talk about elastic net much or at all in this course, but it's a combination of the two methods. We're gonna show the formula and for elastic net, and that's more or less all we're gonna do on elastic net. And again, the point here is that now there will be no problem in fitting models where number of predictors is bigger than the number of observations. Okay, now we present the formula for, let's start with ridge regression. So ridge regression. And so by the way, I wish I have said, imagine now you're in the context of linear regression. Okay, so ridge and lasso are applicable more broadly than just linear regression, but for now, imagine we're in the context of linear regression and we have this problem that we have too many predictors. So we now have a new quantity to minimize under this so-called ridge regression. And the quantity is given here. So let's review this formula, this equation. The first part, this is exactly the same quantity you would minimize under normal or regular linear regression. Okay, this is just the residual sum of squares. Your values minus their prediction, and you want to make that as small as possible. And so you minimize this, of course, as function of the betas. So you find the betas that make this quantity, residual sum of squares, as small as possible. But now, with ridge regression, we add this term, which you can call a penalty. It's a penalty that is going to shrink the betas, make them smaller, smaller on average. And let's convince ourselves that this is indeed, it will have this effect. Well, there's this lambda here that's the parameter. So we're going to discuss how to pick the right lambda a bit later. But for now, just view this as a number, like it could be 0.5, 1, 2, etc. This is just a number. And then we have the sum of all the squares of the betas. Now remember, the objective is still to minimize this whole quantity. So you see, because we add this term that is strictly positive, because yeah, it's the square of the betas, this is going to have the tendency to make the whole quantity, the whole thing bigger. So because we want the whole quantity to be smaller, this will force the new solution, okay, the new betas that minimize the new expression, it will force the betas to be a bit smaller than what they would be, or even a lot smaller, depending on the specific lambda. Well, yes, because imagine you don't have this part. Well, then the betas can be big. Like there's no problem in the betas being big as long as this quantity is small. But now, if you add explicitly that this is in your quantity to minimize, well, if the betas are too big, they're not going to minimize the whole quantity. Okay, hopefully that's more or less clear that yes, adding this penalty will force the solution to have betas smaller than what they would be without the penalty. So yeah, this is what it says here. The shrinkage penalty restricts the growth of the coefficient estimate. Now, um, um, to make this clear, or another way to see it is imagine imagine lambda was zero. What would happen then? Well, if this is zero, you fall back on just your old minimization problem. So this you would have the least square minimization as in regular linear regression, and so um, you will find the same solution, right? So I'm just saying the edge case lambda equals zero, you fall back on your just good old least square best model. The other edge case or limit case is if lambda is extremely large. Well, if lambda is extremely large, and remember, you're trying to minimize this whole quantity. Well, if lambda is like billions of billions of billions, well, the only way this thing will be small is if the betas, all the beta j's are exactly zero. So that's another extreme case. If lambda is very large, well, then all your betas will be zero. Because by the way, important to note here, we start the sum at j equals 1, right? So here we're summing the betas that are the coefficients of the predictors. There's no beta 0 here. So the beta 0 is here, but it is not here. So we're not, in other words, we're not forcing the intercept to reduce because that wouldn't really help in any way. Okay, so we're trying to constrain the effect of the predictors on the response. Now, just a word, because I said it might not be clear why it makes sense to do this. The intuition, I think, is this. By restraining the coefficients, by making them smaller, you force your model to really pick the predictors that are the most significant. So you're in some sense making your model more efficient by really focusing on the predictors that have the most impact in the model. So that's at least part of the intuition why this method makes some sense. But yeah, let's finish explaining this theoretically and then jump to examples. So this is what we're minimizing under the so-called ridge regression. Now, if you've understood that, you will understand the lasso the same way. So lasso again is an alternative approach to this shrinkage idea. Really similar, but the penalty is different. So now what we minimize under the lasso is as before the residual sum of square to which we add the penalty, but now the penalty is again a positive function of the coefficient, but it's not the square anymore. We take the absolute value. So we take the absolute value. So again, we're adding a positive quantity, and you see same idea. We will force the betas to be smaller than what they are without the penalty. Well, yes, because we're adding a positive quantity that to something that we want to minimize. So it's going to force the betas to be small. Now, there's one big difference conceptually or in the results maybe between ridge and regression, and we're going to illustrate that, which is this. Here, under the lasso, you can theoretically force some betas to exactly zero. So it's not only that some betas are going to shrink to very small quantities, some will actually, in the new optimum solution for the betas, some will actually be zero. Now, why this is, frankly, it's not obvious. And you can prove it a bit later, or at least at the end of the lecture, we'll give you a bit of an illustration for the intuition of why is it that the lasso makes some betas exactly zero. But we'll revisit that at the end. And so, yes, you could say that the lasso performs variable selection, like as we've done before, kind of manually, because it forces some betas to zero. So if the betas are zero, it's like you remove them from the model entirely. Okay, and here I don't think I said it before, but in the previous slide, but this is just a bit of terminology. It's also called L2 regularization because the penalty is the square of the betas, so it's the L2 norm. But I think for us those terms don't matter too much. Now, an important note about those methods. Before you apply your ridge and your lasso to your data, you have to standardize the x's. I mean, I say you have to. It really is the common practice. and it's especially true if all your x's are measured in different units, which most of the time it will be. Okay, so really, unless you have good reasons not to, based on a very specific context, almost always, when you apply ridge and lasso, you standardize your x's. Here, standardize x's columns, meaning that the columns represent different predictors for all the observations. You want to make those predictors to have a mean of 0 and a variance of 1 before you apply the ridge or lasso. Now, why is that? It's because otherwise, how to say, if the units of a given predictor are such that the betas are already small, well, and other predictors have units that are such that the betas are big, um, you're not comparing apples to apples here. So let's give a simple example. Okay, imagine one predictor X is an amount of money. Now imagine, so you can measure money in different units, right? You can measure money in dollars or maybe thousands of dollars, right? So imagine first scenario that X is coded in thousands of dollars. So the units of X are thousands of dollars, meaning X equals 1 means $1,000, right? Now you fit your linear regression, and for this specific X, for this specific predictor, you get a beta of, let's simplify our life here. You get a beta of 1. Okay, beta of 1, which means, remember, the units are thousands of dollars. So the interpretation is this: if X increases of 1, Y increases of 1, because beta is 1 instead of the Y. And imagine here that Y is, again, measures in thousands of dollars, right? Thousands of dollars. So here we're saying, okay, when X increases of $1,000, on average, Y increases of 1,000, and beta is 1. Now, imagine you have coded this data differently, and the X's are now in dollars, not thousands of dollars, okay? Meaning X equals 1 means $1. Now, you refit your linear regression model. What happens to beta? And you haven't touched Y, so Y is still coded in thousands of dollars. Well, your beta is now 0.001. Well, yes, because you should have the same effect. It should be that now, if X increases of 1, remember now it's just $1. Well, Y is going to only an increase of 0.001. Well, because Y is still measured in thousands of dollars, right? So, but the effect will be the same on Y, meaning if this new X now measured in dollars increases of 1,000, then 1,000 times the beta coefficient of 0.001 will give you a unit of 1. So yes, again, your Y has increased of $1,000. Again, in this example, remains, the units of Y remains thousands of dollars. So you see, in one example, the beta is 1. So it's, you could say it's large. In the other, just because you change the units, the beta is already super small, 0.001. But so to make the method make any sense, you should transform the X's or standardize all the predictors. So they have a mean of 0, they have a standard deviation of 1. So then you can always interpret in the same way that, yeah, a beta of 1 means that when X increases of 1, when X increases of 1 standard deviation, then Y increases of 1 with it. Okay, hopefully that makes a bit of sense. So yes, do standardize your X's. Now I say all of that, but in reality, we're going to use the package GLMNet, and GLMNet does it for you by default. So you need to be a bit careful. It's going to do it by default. You feed it data. We're going to see examples of that. It's going to automatically standardize it before applying the lasso. Okay, this is a slide on what I mentioned before. We're not going to say too much about elastic net. So elastic net, again, you would minimize a quantity, which is just the good old residual sum squared, but plus a penalty. But here the penalty is a bit of ridge and a bit of lasso. Okay, so now you have the same lambda that for now is a bit mysterious, but we're going to explain it soon. But then you have also alpha, and so now part of the penalty is lasso. The rest of the penalty, okay, alpha would be between 0 and 1, so the rest of the penalty would be ridge. Now, we kind of need to know this at least in R, because the package we use is GLMNet, net would be for elastic net here. And so this package in general does the elastic net, but we can recover ridge and lasso, of course, by having either alpha equals 0. So alpha equals 0 here would be ridge, because this term would be the ridge one. Or if you want lasso, you just use alpha equals 1, in which case this term disappears and you fall back on your lasso. Okay, now just here there's a bit of terminology. Usually when we say ridge regression, we mean good old linear regression with a ridge penalty. So ridge regression would be, well, will be this, minimize this. Likewise, if we say lasso regression, we mean linear regression with a lasso penalty. So we mean minimize this. But this idea, more than a specific model, it's more an approach to modeling or a tweak on existing models. So this idea, you can apply it to GLMs at large. Okay, so you could apply it to logistic regression, to Poisson regression, or any GLM, and the package GLMNet allows you to do that conveniently. Now, just a note that, well, in that case, remember in GLM, when we do the fitting, we minimize something called the deviance. So same here, the penalty in the case of a lasso or ridge GLM would be added to the deviance, okay, rather than the RSS. But conceptually, it's the same. You want to shrink your parameters, so you're going to add a penalty now on the deviance. Okay, because again, the deviance, you want to make it as small as possible, but now with the additional constraint, you could call it that the betas shouldn't be too large. Okay, here, just a bit of an example. In R, so we're still using the, this is as before, the rank, overall rating of people working at different universities. But now we're using the data set that has only 3 rows. So again, same thing, we obtain just the first 3 coefficients when we do regular linear regression. Now, you might try to, so remember, because remember, this is the theoretical solution for the betas in linear regression. So R doesn't give it to you. Now you might try to find it yourself, like by implementing this formula, which is done here. So we're going to solve the transpose of the matrix times the matrix, solving finds the inverse, but there's no solution. There's no solution because, well, because this matrix is not full rank. Well, again, because you have too many predictors. Now, ridge as a solution. As a solution, and it's a simple in some sense because it's really a tweak on the solution on the linear models. We don't present the proof here, but the solution for the betas on the ridge penalty is the same, but here we're adding the lambda in the penalty term times the identity matrix, and we add that to the usual x transpose x, and now we take the inverse. And this addition of a small numbers on the diagonal actually makes this matrix invertible. So now we have a solution. Now again, we skip over all the technical details for that. It's just more for your information that the ridge has a closed neat solution there. And so here now you can solve, and again with the same data, and you're going to get, so here on the right we're doing this manually, solving t transpose x times, here we're arbitrarily choosing a small lambda of 0.01, you get a solution. On the left, we're doing this with the GLM net package. Now I'm going to explain the syntax. Well, I can explain it now, it's pretty simple. You need to feed the design matrix, okay, the big X matrix, but without the first column that has all ones. So remember, the design matrix here, X bold, the very first column is all ones. So in the syntax of the GLM package is you need to feed basically you just need to feed all the columns for your predictors, but without the intercept, so without the 1, 1, 1, 1, 1. So this is why we're removing the first column here with the syntax -1. The second argument would be the y, so the vector of y values. And then that's it. Here the alpha is 0, means, remember, the ridge. Alpha equals 1 would be lasso, and any alpha in between is elastic net. You give a specific lambda. And here, by default, standardize is true. So that's what I said before. By default, standardize is true, which is the correct thing. but you can force it to be false. Now, the reason I'm forcing it to be false here is simply that on the right here, I haven't gone through the trouble of standardizing the columns, right? So I want to compare apples to apples. So if I'm not standardizing with the manual solution on the right, I don't want to compare it to a standardized solution on the left. Now here, if you have a good eye, you might see that the coefficients are slightly different. They're close, right? 4.33 and 4.32. Yeah, they're close. They're not exactly equal. So I'll be honest. I don't know why. Okay, I don't know why. I would have imagined that the package here is implementing the exact solution when one is available, but apparently not. So I don't know. I don't know why. Like it's very close. I'm not gonna lose sleep over this, but I haven't investigated why the package doesn't give you the exact solution here. If some of you want to go on a side quest and figure out why there's a difference between the package and the closed solution, be my guest and inform us on the discussion forum of the result of your quest. Okay, that's all the explanations. Let's illustrate this with a few different examples. So frankly, most of the rest of the lecture is illustrating those two methods, Lasso Ridge. Here we focus on visualization, and in the next section, demos, we're going to focus on the R code. So here we're going to use a synthetic data set. So we've ourselves generated just y function of x in a nonlinear way. So you see it's a quadratic form. Now, by the way, on the website, you have all the code to generate this example and apply the lasso. I'm not going to focus on this code, but it's available on the website. When you go to this section, you can unhide the R code. Okay, so that's the situation. The green curve is the real curve. Okay, so again, we generate this data, so we know exactly what the correct function that links y and x is, which is the green curve. But around it, there's noise, right? Because we usually in reality there's going to be noise around the pattern. So here we generate our data with some noise. Okay, now what we do here is that first we're fitting to this data what you can call a polynomial regression with lots and lots and lots and lots of terms. And we're going to see that this is a bad idea. It doesn't yield a good fit. You could say it's overfitting because you have way too many predictors. By predictors, what I mean here, because you have just one x and one y, but you see here just linear regression in the sense of y is a linear function of x would do a terrible job, but you can add predictors that have the form of a power of x. So you can try, okay, I'm going to try to explain y as a function of, yes, x, but also x squared, but also x to the 3, but also x to the 4. And let's just say that a priori, we don't know how many polynomial terms we want to include. So we start with kind of way too much. Okay, so here for the illustration, we start with 20. We start with 20, so with this data set, again, I'm not showing you the code, but if you fit the data to 20 predictors, all of the form x, x squared, x to the 3, x to the 4, up to x to the 20, this is the fit you get. This is the fit you get. And the fitted curve on this plot is the red one. So you see, it's pretty terrible in the sense that it's finding patterns that really don't exist. And yes, here, yeah, to 20, up to the power 20 is just way too overkill. So you get a bad fit. But the point here is this: the sum of your betas, the sum of the beta squared here is huge. So the actual sum of all the betas for all the predictors is this huge number, 6 million something. And so here we're going to apply the idea of ridge, first ridge and then lasso, to say, okay, if I'm going to do the same thing, I'm going to still keep 20 predictors, but I'm going to shrink their coefficients via the ridge penalty. What's going to happen? Okay, well, already we can give you the punchline. With even just a small penalty, okay, just a small penalty of lambda equals 0.01, we have increased, we've improved the fit like dramatically. Here, the red line was absolutely bad, at least bad for the small x and large x. Okay, I guess not that bad on the middle. But now, just applying the ridge with this penalty lambda equals 0.001, there the fit looks pretty good. I mean, maybe not perfect in the sense that it's not exactly on the red curve, but it's good. And you see, Here, this is the equation fitted now under the ridge. That's the point. Some of the coefficients are now extremely small, though not exactly zero. And we're going to contrast this in a second with the lasso that's going to make some coefficients literally zero. Now, what I said before that is a bit mysterious is how do you pick the lambda? It's just, is it just any lucky guess? You pick your favorite number? Of course not. We're going to explain soon how to pick lambda, but for now, just for the sake of illustration, we show you different lambda. So here, with lambda equals 0.01, which remember is just a small penalty, we get this. Lambda equals 0.1, so a slightly bigger penalty. Maybe it's a bit better, but it's a bit hard to really decide which is best. But it does look like here, lambda equals 0.1 is doing an even better job. So yeah, this blue line, which is the fitted line under the ridge, is close to the real line, which is the green one. And again, some coefficients are now extremely small. And you see now the sum of the betas is much smaller. Although yeah, sorry about that. I realized this. Pretty sure that here in the first one, the naive just linear regression. Pretty sure we had not standardized the x's before we apply this. So now we get this sum that is really huge, but we had not standardized the x's. But just believe me that if we had standardized the x's before applying just linear regression, we would have gotten a sum here that would not have been as huge as this, but still bigger than this for sure. And this. Now let's keep going. Okay, let's increase lambda. So again, when you increase lambda, you increase the penalty, so you shrink the coefficient even more. And now we start to see that, okay, if lambda is too big, so too big a penalty, we're not going to get something that's amazing, right? We're not going to get something that good. I mean, I suppose it's not terrible yet, but we are getting the fitted line, the blue one, is kind of departing more from the green one, which is the real theoretical one. And we try one more time. Again, increase lambda even more. Penalty is too big. You're shrinking the coefficients too much. And now you get yeah, an even worse fit. So you see, you need to conceptually you need to play with the lambda a little bit to find a lambda that is in some sense optimal. Yeah, and just here conceptually, recall that lambda extremely large means that you're going to force all the coefficients to zero. If you force all the coefficients to zero, aside beta zero, which is the intercept, which is unaffected by the penalty, what's going to happen if lambda is extremely big? Well, you're just going to fit a straight line, a horizontal line. You're going to say the fitted value for every point is just the mean of all the points, which it looks like it's going to do something like that. If you keep lambda, yes, you're going to get this curve is going to eventually be very flat. Okay, this is the so-called regularization pot plots. To have an overall idea of what's happening, as you increase lambda, you make the penalty bigger, you shrink the coefficient more. So this is like a snapshot of what's happening. On the y-axis, you have well, it's not lambda, it's log of lambda, but using log of lambda in those illustration plots usually leads to better better visualization. So but as lambda increases, of course, log of lambda increases. So as function of here lambda or log of lambda, what's the actual values of the coefficients obtained in this ridge regression? Well, you see, when lambda is small, you would get the coefficient you would get under just regular linear regression, and as you increase lambda, the penalty is bigger, so the coefficients are going to shrink. And if lambda is very big, well, then you force all your coefficients to zero. So overall, this is what is happening. Now, on the top, you see there's the number 20, 20, 20, 20. This is the number of coefficients that are not zero. On the ridge, we expect that the coefficients are going to shrink very close to zero, but never reach zero. And this is indeed what we obtain. So the number of non-zero coefficients stays 20, regardless of what lambda is. So it's not especially helpful here, but under the lasso, we're going to see that those numbers are going to be a bit more, meaningful. Okay, so now I forgot this is what's presented already here. how do you pick lambda? How do you pick the optimal lambda that will yield the best predictions for your lasso or ridge model? Well, this is where we make a link with the first part of this module. The answer is, everybody says together, cross-validation. Well, yes, cross-validation allows you to, in some sense, test which lambda is best, which leads to the best, well, to the smallest mean squared error, what we call before the cross-validated mean squared error. So, well, yes, imagine you have your data set. Okay, as I explained in the cross-validation part of the course, a good practice to set aside what was called a test, okay, the test data test set, and now you're left with a substantial chunk of your data. You can use it well, yeah, to use cross-validation to pick what lambda is the best, because for a specific lambda, use cross-validation to find the mean squared error on this subset of the data. Again, remember for example, k-fold cross-validation. You have your data set that you split in different chunks, and then you use in turn each chunk as a training data and validation data, and so on. Doing that, you get an estimate of the mean squared error for a specific lambda. You will get some number. Do it again with a different lambda. You get a different estimate of your mean squared error. Do it again, do it again, do it again. You do this for a whole range of lambdas, and you can see, okay, there's a certain lambda that gives me the best mean squared error, cross-validated mean squared error. So cross-validated mean squared error means it's an approximately unbiased estimate of the real mean squared error. Again, this is the topics covered in the first part of the lecture. So this is what is illustrated here. Again, there's an R command or R function that does this for you. But overall, what's happening? We're saying that as function of log of lambda, the mean squared error here, cross-validated mean squared error, is essentially increasing. Now, the first line is actually the minimum. So there are such values of log of lambda smaller than this minimum, such that the mean squared error is a bit worse, a bit higher. But here in this specific example, it looks like the best mean squared error, cross-validated mean squared error, is obtained for a small value of lambda, which matches. So again, this is the same synthetic data set, matches what we saw here. It looks like 0.01 is already very good. Maybe 0.1 is a bit better, but then it gets worse. So yes, it looks like, sorry, I went too far. Looks like a small, so again, this first dotted line here is where the lambda that yields the best mean squared error is. And here in this specific example, the R package will tell you that the lambda which minimizes here in this case, the 10th-fold cross-validation is 0.18. 0.18, which kind of makes sense because we said here just kind of manually 0.01 is already good, 0.1 is better. Okay, we don't have 0.18, but it would be maybe even better. Okay, let's try the same with Lasso. So exactly the same data set. Now again, the Lasso is similar concept, but now we have the penalty is the sum of the absolute values of the betas. Same idea with lambda 0.01, already pretty good fit, pretty good model. And here we tell you, okay, it looks like now there's only 8 non-zero coefficients. So already with a small penalty, we've already shrunk 12 of the predictors to exactly 0, and you just keep well, in this example, there's only 8 apparently that are non-zero. If you keep going, okay, lambda equals 0.1, okay, fit looks pretty good. And here actually, with the penalty lambda equals 0.1, already we've eliminated pretty much all the useless predictors. Yeah, two okay, already with lambda equals 0.1, only two coefficients are non-zero, and they are the two first ones, the x and the x squared, which it's not necessarily the case. Like you could have gotten that the only two that are left significant is x and x to the 4 or whatever. In fact, here apparently, yeah, apparently out of the 8 that remain significant, you see there's dot 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 here, but the x to the 19 for some reason was still significant, and x to 20 was still in the model, albeit with very small betas. Same thing, if you keep increasing lambda, eventually the fit gets worse, right? So with lambda equals 1, you actually keep only one non-zero coefficient, which would be the x to the 2, but now the fit is looking worse than with two predictors. And in fact, maybe I should have said this from the get-go. This data was generated following some curve like that, some formula like that, meaning only a x and x squared terms are in the, well, are the function that really generated the data. Okay, and again, if lambda is big, you get a straight line as a fit. Okay, still one non-zero coefficient, but actually the beta is essentially zero, so it's a straight line. Okay, so the equivalent to regularization pad plots. Now it's a little bit more helpful in the sense that as function again of the log lambda, which don't be confused here, it's negative, but log of lambda negative can still mean that the lambda is positive, just small. You see on top, you see the number 11, meaning that for this specific log lambda, there's still 11 non-zero coefficient, but then lambda increases, you get only 8 and 5 and etc. Eventually, lambda is big enough that all the coefficients have been forced to 0. Cross-validation error. So we see here, same kind of thing. If you do k-fold cross-validation, you can identify the lambda that gives you the smallest estimated mean squared error. And in this case, it looks like, well, it looks like for lots of values of lambda that are small, you get very similar mean squared error. Theoretically, not theoretically, but technically, the smallest is this dotted line here. And by the way, the second line here that they give is one standard deviation away, from the minimum. I think this is explained a bit later, so I'll pause on that. But just if you're wondering why there's a second line, you see there are some errors. Okay, the red dot is the estimated mean squared error, but the package also finds some standard error on the mean squared error estimate. And so basically the second dotted line is one standard error away from the minimum. Again, we'll revisit that probably in a second. Okay. This is all the illustration of the concepts. And especially that in practice, you could have some guess of the lambda initially, but you can try many, many different lambdas, and via cross-validation, you find the one that leads to the cross-validated smallest mean squared error, and that's a good way a good way to pick your lambda. Pick your lambda for your kind of final model. So now let's actually do it in R, showing you the commands. They're relatively simple, but you do need to be a bit careful, I suppose, with the syntax. So okay, first example is again the so-called glass door data set. So here, what are we doing? We create a new model, just the linear model, where the overall rating, so overall how they like their employer, is going to be explained by all the variables we have, actually. So the work-life balance rating, culture values, etc. But we're also putting in here the whether or not they recommend this company and whether or not they approve of the CEO. So basically, we create a new model because before in the first part of this module we had two competing models. Now we just put all the variables together and we create this model. This is just as we've done in the first few weeks of the lecture, just standard linear regression. And you see, okay, we have a decent R squared and most essentially all of those coefficients are significant based on the p-values. But now we're going to apply Lasso and Ridge to this data set. Okay, let me just take a sip of my beverage. I hope not to lose my voice again by talking so passionately about Ridge and Lasso. Okay, first off, we will just fit the ridge and plot those so-called regularization plots. Now, the function we use is glmnet. Now, by default, GLM is just going to assume linear regression with Gaussian response. So if you don't change any of the arguments, this is what it's doing. The glmnet will just fit a linear model, but with either a ridge or a lasso penalty. I mentioned this because you can also fit a GLM more generally. This is why it's called, well, GLM here. Okay, but if I type sorry, I should have shown you here the code. So we need to prepare a little bit of data. X, I think as I've told you before, needs to be a matrix, and matrix is a certain type of object in R. The matrix of where all the columns are represent predictors and the rows represent different observations, but without the first column that has all 1, 1, 1, 1. So a very useful function in R is this model.matrix function. If you feed it the equation of a linear regression, so overall rating would be our y, and all those variables would be our x's. We feed it the specific data set we have, which is our here. This is what we've called before training and validation set. So, meaning we could have set aside a test set as the very last step. If you recall, where we can estimate the final mean squared error of the final best selected model, but everything else is in this data set that we call train and val. Okay, so both training and validation. Okay, so having done that, so this is our X. Again, the design matrix without the first column with all the ones, and Y is just the response. Okay, so one is just in this case, the response is the overall rating. Again, for our data, here the data is training and validation. Now, where was training and validation defined? I suppose it's the same training and validation data set as as we defined in the first part of this module. Okay, so now because we've done this good work of defining the X as the design matrix without the column of ones, and Y is just the response, we can just have a simple syntax for glmnet X, Y, alpha equals 0. Alpha equals 0 means elastic net. And now, okay, here we haven't specified the lambda. By default, if you don't specify the lambda, R uses a series of kind of automatic lambdas, right? So it has itself a way to pick which lambdas make sense for the specific data set, but you can force it. So here, if you were to type lambda equals 0.1 or a vector of 0.1, 0.05, etc., you could force the specific lambdas that you want. Otherwise, just let R decide, and that's fine. And then you can plot ridge. Here's the name of the model. There's a few arguments here to tell it that, okay, you want the log lambda here. Labels equals true. I think it's just the number of the variables here. And this is what we've seen before. As lambda increases, the coefficients are shrunken. I forget my irregular verbs, but I've studied this in Canada a long time ago. Anyway. Okay, now there's another function. So this is kind of if you want to fit one ridge model, possibly with different lambdas. But there's another function that you need to use if you want to do the cross validation, which in practice you probably want to do, which is the cv.glmnet. Okay, so careful. Here we had glmnet, and now we have cv.glmnet to do the cross-validation. And again, this is used to pick the right or the best lambda. Now you can okay. There's an argument endfold in this function. By default, endfold will perform the cross-validation on 10 folds. So again, splitting whatever data you feed it into, well, 10 folds, each with 1/10 used as validation set, and then the rest used as a training set. And doing this 10 times, and then taking the average to find the estimate mean squared error. If you want to change that, you can. Here, I haven't specified it, which means that by default, I'm going to use 10 folds. And that's it. Other than that, it's the same syntax. You feed X, you feed Y, alpha equals 0 means ridge. And now plot, if you apply plot to this CV, now you don't get the same thing. Now you get this illustration of, okay, the mean squared error is, well, is increasing here in this specific case with log of lambda. Now, you might think, okay, it looks like a mean squared error is always increasing as a function of log of lambda. It's true in this example. It's not always true. So let me just jump forward just to show you where. Okay, so here, this is what you could get. Okay, and maybe this is more typical, at least when you have lots and lots and lots of predictors. You will see that the well, this is a binomial model, so it's not the mean squared error anymore; it's the deviance. But the idea is the same. It's not necessarily true that very, very small lambda are always the ones that yield the best predictions, right? So here in this case, you have a sort of U shape. So yes, you increase lambda, it helps your model initially, and then eventually it's no longer good to increase lambda, right? So I just want to show this that you can, depending on the data, there's different shapes you can get for this, well, for this mean squared error as function of lambda. Okay, but in this case, going back to the example, where was I here? Again, for this real data set, the function cv.glmnet has found through cross-validation that the optimal lambda is this one, 0.08. So again, that's a log value of minus 2.53, corresponds to the first dotted line here. Now we do the same with the lasso. So conveniently, we can use the same formula or the same function. Lasso would be alpha equals 1. Plot lasso, same thing again. Here, some coefficients are literally forced to 0. So again, on the top, you see we start with 9, but eventually, if lambda is big enough, we're going to force some coefficients to exactly 0. So we'll get to 8, 7, 6, 4, and so on. If you want to find the optimal lambda, you use, again, cv.glmnet, x, y, alpha equals 1. And then you plot this object CV lasso, which is your model, and then you get, again, looks like the optimal lambda is, again, on the smaller side of the spectrum that is tested, which, again, R, with this function in R, as a way to assess the large spectrum of possible lambdas that are not always the same for different data sets. Frankly, I don't know how R picks the correct range of lambda that it's trying. But if you want to manually specify in this function glmnet what lambdas to try, there is an argument to do that. Oh, sorry, I forget the name of the argument. Unfortunately, I'm not even sure it's called lambda, but yeah, well, you'll need to double check this. It's explained in the book, at least. It might be called S or something. Yeah. Yeah, but anyway, the bottom line here is that again, we get that the optimal lambda is for well, for what seems to be a pretty small small lambda, so a pretty small penalty or shrinkage of the coefficients. Okay, now we explain a little bit this business of having a second line here, which I don't know how how used this is in practice. Frankly, I don't know, but it's implemented in a package, so it looks like the author of the package think this is a good way to do your fitting. Um, so, okay, let me just read what's written here. Lambda min uh, uh, in this R function is what we said, the lambda at which the smallest MSE, cross-validated MSE, is achieved. Uh, and again, shown as the first dotted line on this plot. But there's also the lambda 1SE for one standard deviation, which is the largest lambda at which the MSE is within one standard error of the smallest MSE. So what does it mean? Well, here maybe this plot is not the best to see that. Let's go to again. I'm going forward here. Okay, in this example, it's a bit better because the errors are wider. You see, the first line is here. So the red dot is the estimated MSE, but R also somehow computes a standard error for this estimated MSE. So R is saying, okay, one standard deviation higher would be here. Uh, so basically, it's plausible that the best lambda has MSE as high as this value. So then if you go from this point and you go right, and you're gonna go, okay, follow this line. Okay, let's say that I'm doing this properly and I go from this height here from this bar and I go right, 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 right. I'm gonna find a lambda whose estimated value is here, right? Because as lambda increases, the MSE increases, but we're basically saying it's not far-fetched here to say that um, the, 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 the MSE of the correct value for lambda is at that value. And that value of lambda is higher. But a higher value of lambda means a higher penalty, so more shrinkage, more regularization. So all I'm trying to say here is you could prefer more regularization because more regularization means you're shrinking the coefficients more, you're making your model in some sense more parsimonious, especially with Lasso. Okay, especially with Lasso, you're forcing more coefficients to be zero. So it could be that you have a preference for a model with more regularization. So it could make sense that you're going to pick the lambda that is one standard deviation away from the minimal lambda, and that's the lambda that you pick. Okay, so it could, or at least the authors of the package here, um, they are saying this is a possible way to pick lambda. Okay, don't pick the one that is the minimum, but you can go up to one standard deviation away and pick that lambda that gives more regularization. Now, I'm not telling you should do that, but I'm just saying that's a reasonable thing to do if you want more regularization. Okay, so here, and this is illustrated here. If you pick lambda min, okay, the lambda that technically gives you the smallest MSE, you get this coefficient is 0 and this coefficient is 0. But if you pick one standard deviation away from that, you get more regularization because you have a bigger lambda, and then suddenly you get more coefficients that are forced to 0, and then maybe you're happier with this model because it's simpler. You have fewer coefficients included. Okay, I hope this made a little bit of sense. And now in terms of R syntax, not especially complicated here. You have this function coefficients applied to your fitted model will give you, well, will give you the specific coefficients, function of the specific lambda. Here again, I don't know why this is called S and not lambda. Maybe there's a reason, but yeah, well, we're basically saying for the specific lambda, that is the lambda min as illustrated here, those are the coefficients we get under under Lasso here. Okay. Now, this is an example where, frankly, maybe regularization is not really relevant because your linear regression, most of the coefficients were significant, and this is a case where linear regression is fine. You have way more observations than predictors. so those examples are more to illustrate the mechanics of how this all works, how we do the fitting. But frankly, for this glass door preparation, at least I personally quite like linear regression here. All the coefficients are very significant. Um, I mean, yeah, and I haven't done it, but we could do it. We could check if the mean squared error on the test set uh, has improved under Lasso and Ridge. We haven't done it here. Um, my intuition would be that Lasso and Ridge is not going to improve the mean squared error on the test set. This little bit we set aside for the kind of final choice. Yeah, yeah. If I have time, maybe I'll do that and double check. But my point is just this. Now we're going to see an example where you need Lasso. You need Lasso or Ridge because you have way more predictors than observations. And this is this genetics data set. Now, uh, it, okay, on the website, you have code to generate this data. Frankly, it's a bit complicated, and that's not really the point here. We just want to illustrate a data set with lots of predictors compared to the number of variables. And I myself don't really understand this genetic stuff that I cannot really interpret those the predictors. I think there's something called gene expression. So there's some measurement of how the gene is. Frankly, I don't know, right? But you just need to know that those are numerical predictors. You have many of them, thousands, but you only have, I believe, 99 subjects here. The 99 women. This is described here. We can maybe review this small paragraph. Okay, so from this academic paper, described breast cancer study with 99 women divided into two groups according to their estrogen receptor status. So here, again, I'm not going to pretend I understand medically what's happening here, but for us, in terms of predictions, this is going to be classification problem because you have only two possible status. So the estrogen receptor status is either 0 or 1. So yes or no. And so this is what we're trying to predict. Yeah, okay, so this is the ER, stands for, I suppose, actually, I'm not even sure. Receptors, maybe estrogen receptor. Doesn't matter. We just have this response is 0, 1. Out of 7,000 something variables, there were 4,000 something that had a measure for the 99 sample. So here, again, the bottom line is that we have a data set that is very wide. You have only 99 people, but each of them, you're measuring this gene expression thing on 4,000 something, I suppose, different genes. So you cannot do linear regression, okay? Because number of predictors is higher than observations by a lot. But you can do your Ridge and Lasso and try to obtain some meaningful results. So let's do that. Okay, so let's take it from the bottom. We will set aside a test set. And again, this is for the final estimation of the mean squared error of the best model we're going to pick because we're going to try a few different ones. Okay, so the test set, well, this is the index, so the numbers of the rows that are going to be in our test set. Okay, we take just 20% of the total number of rows. So that's a relatively small number here because we only have 99 rows. Okay, so we're taking the index, so we're picking the rows in the initial data set, so that becomes our test set. The training/validation set is everything else. It's everything else. Now we just prepare the data to feed it to GLMNet. So again, this is creating our design matrix. So ER again is the name of the response in the data set. So ER is this 0101 thing. The tail, the dot, in case you don't know yet, it's just doing a regression on every single predictor. So here, this just means ER is my response. My predictors are everything else on the training and validation data. And then again, this is just to remove the intercept. So that's like before. Y will be my response. So this is just the ER variable in my training validation set. And then what else? Well, this is just doing the same thing on the test set. So on the test set, we're gonna find the final estimate of the, well, not the mean squared error, but in this case the test error rate, because it's a classification problem. We do that on the test set. Okay, that's the preparation, and now I believe we can just apply our functions. Okay, well, that's a colorful picture. Remember, we have thousands of predictors. So, but you can still, I suppose, in a snapshot, view what's happening. Again, with your ridge regression. Now, just careful. We use GLMnet on our X, our response Y, but here we use family equals binomial. So that's what I told you before. If you don't specify anything, it's just going to assume linear regression, so a Gaussian response. But if you say family equals binomial, now we're doing logistic regression. Now we're doing logistic regression that we're familiar with since week 3. Alpha equals 0 for ridge. And so here, this is what I said before. Ridge applied to logistic regression, well, would be ridge applied to a GLM where the penalty is the same idea, but we apply the penalty to the deviance of the model. And now we plot this. I don't think I have too much interpretation to give you. Again, same idea. If lambda increases, the penalty increases. Your parameters are shrinking more. What's a bit more interesting is the cross-validation. So here, yeah, again, same function, cross-validation on X, Y, same thing. Our binomial model. Looks like, okay, the minimum is here for log lambda of 2 point something. And again, you could pick the lambda that is on the second line here, 1 standard deviation away, if you want a bit more regularization. But here, I would say ridge is, what's happening here? Okay, so by default, it looks like by default, if you have a binomial model, the criteria you're cross-validating, meaning, well, you compute it for different values of lambda using the cross-validation approach, is the deviance. But if you would prefer the criteria of what we have called the error rate in the case of a classification problem, but here it's called misclassification error. So this is basically just the percentage of predictions that are wrong. You can use that as the criteria on which to pick the best lambda. So this is what is done here. Using type measure equals class, I suppose, for classification. Yes, you will display, again, as a function of log of lambda, what is the error rate of your model. You see for a small lambda, it looks at exactly 20%. Then it decreases a bit. Okay, so it increases a bit for some reason, then decreases, and then you find your minimum here. Pretty sure what's happening. It looks like the misclassification error is constant for different values of lambda, but we're picking the largest lambda such that we have a minimum. So largest lambda such we have a minimum. The logic being that everything else being equal, we prefer more regularization than less. I think that's the idea here. Now, because we have so many predictors, maybe Lasso is kind of better, or at least it's certainly more elegant, because we're going to get a drastic reduction in the number of predictors in the model. Yes, indeed. Here, let's try Lasso. Same code, and so that we write alpha equals 1. What's happening? Well, already with only a little bit of penalty, we drastically reduce the number of predictors in the model, because most of those coefficients have been set to exactly 0. And that might help us for interpretation. I mean, again, if you were a geneticist and you actually know some interpretation of all those gene expression things, and in the end you get a model, let's say that you get a model with 20 or something, but maybe you can actually interpret what they do. If you have thousands of them, very hard to interpret anything. Okay, so that's the snapshot. So here again, minimizing the the cross-validated deviance, yes, you would obtain your optimal lambda to be again the first dotted line here. Okay, you will get, because it's a different criteria. If you want to yeah, minimize the deviance is not exactly the same thing as minimizing the misclassification error. So you would get a different lambda if instead of deviance, you have the measure here classification error. But you can do that if that's what you care about. And again, you will get the new lambda. That for some reason I think would be less parsimonious here. It looks like you keep 35 predictors instead of 22. Okay, and then the last step, which is important if your goal is to pick a final best model. Here, what we do, we compute the test error on this test set that we've set aside. Okay, so well, let's review that. Now here we just have two candidates models. We just have Ridge and Lasso. Well, yes, we cannot have linear regression because we cannot do the fit with linear regression with so many predictors. So let's try. Okay, CV Ridge was our fitted ridge. We can extract from it an object called CVM, should stand for classification, I suppose, classification error. Cross-validate, sorry, CV cross-validated M, what would be M for? Probably, yeah, there's an M here, misclassification error. So, I mean, that would be M, I guess, that this stands for cross-validated misclassification error. In the case of Ridge, we get this number, 0.1875, which should correspond to what was on the plot over here. Where was Ridge? Yes, this line here looks to be a bit below 0.20, so it would be this 0.18 something. Lasso looks better, right? Lasso looks like we've have a smaller error in the case of Lasso, 0.1375. How many coefficients do we have if we use lambda min, so the absolute minimum of the lambda, when we're minimizing the classification error? This is this number here, 30 something, 38 apparently. But if you use 1 standard deviation away, actually, yeah, now you get way fewer predictors, which maybe you might be happy about to trade. You see, to trade a little higher mean squared error, but again, the point is still within those confidence bounds for the one that is the smallest. And here you would trade, you trade a higher misclassification error for way fewer predictors, which you might be happy about. And here there's just a little bit of code. Now here it's not that helpful here because you only have two models, but if you have many models, then picking the best one, you might do it with some sort of automatic procedure in R. But here we're just saying, okay, if the Ridge cross-validated error is smaller than the Lasso one, then the best model will be called CV Ridge. Otherwise, and model type is Lasso, else best model is CV Lasso, model type is Lasso. Okay, but again, the relevance of this in this kind of manual example where we only have two cases, it's maybe limited, but in the end, print paste the selected best model is my model type as defined here, either Ridge or Lasso. And in this case, yes, Lasso. This just means that this number is smaller than this number. But lastly, the last important step, let's compute the approximately unbiased error rate of our best model. Yes, now this is the only step where we use our test set, what we saved aside for later. Okay, this function predict, you feed to it the name of your model. Now, this is best model because I've defined my best model to be my Lasso in this specific case. So this is the name of your fitted model. You feed it the new data set, okay, a new data set on which is going to compute the prediction based on what the model is. So here this was called X test the very beginning. Okay, the type is response, but response, because this is a logistic regression, the response is going to be the probability. So careful with that. The response is the probability, so a number between 0 and 1. But now we transform it to prediction. So remember, in logistic regression, the default is that if the estimated probability to be 1 is bigger than 0.5, I mean, 50%, you code it as a 1. And this is what we're doing here. So here, careful with this syntax, you get the probabilities. Now, bigger than a constant, this is a vector of probabilities. All your fitted probabilities on your test set. Bigger than 0.5, this is going to transform the vector of values into true, false, true, false, true, false. True if a given probability is bigger than 0.5 and false otherwise. Now, the object called test accuracy here is going to simply be the proportion of correct predictions. Proportion of correct prediction, this is sometimes called the accuracy of a classification model. So this is our accuracy on our test set. How this is computed, it's a bit clever. You take the mean of the actual responses on the test set being equal to the predictions. Now this works because this is a series of 0, 1, 0, 1. And now I just told you this is now a series of true, false, true, false, true, false. But R, for mathematical computation, R views trues as ones and false as zeros. So this code works. It's comparing, it's checking, okay, R is a 1 here, also a 1 or true here. If yes, you're going to get well, this is an element, it's comparing two vectors element by element. So whenever the test actual value is the same as the prediction, you're going to get a 1. Otherwise, you're going to get a 0. And if you take the mean, yes, you get the proportion of correct predictions. Again, if you don't believe me that this syntax works, well, try it out for yourself, okay? Try it out for yourself. This gives the proportion of correct predictions. And so at the very last step, we're going to output 1 minus that. So 1 minus the accuracy gives you the error rate. And here you see 0.16 or something like that. Not too far from this number. But recall, because you've specifically picked the best one, this is not an unbiased estimate of the error rate of your best model. This would be the very last step. This would be the unbiased estimate of your error rate. Frankly, if you have only 2 models, I suspect this value is not that biased, but it becomes a problem when you have many models. You pick the best one. Well, the mean squared error or the error rate of this best one then is biased as an estimate of the real error rate of this model. But anyway, that's all the fitting and R commands. You'll need to try it for yourself in the tutorial problems, maybe in the story wall. If you have difficulties with those R commands, ask us for clarification. I do see that it can be a bit confusing at first, so many different R commands that maybe you're going to be frustrated with because it's not going to work straight away. Maybe R is expecting a matrix and you don't feed it a matrix, so it's not happy and things like that. There's no easy solution to that. You really need to try those things. Hopefully the tutorials help with this. Now, just a few more minutes, I suppose. There's just a few more slides to come back to the intuition of why Ridge and Lasso make sense or can give you something sensible. Well, maybe just like, let's just explain the situation here using the plot, this plot. You probably don't want to pick a lambda such that your coefficients have shrunken like a lot, because then they're going to be super biased because they're going to be close to 0 and zeros, those zeros will not be the real values. But if you shrink them just a little bit such that you avoid overfitting and they haven't changed like too much, they haven't become super biased, then it can help your predictions. But what is explained in those slides here is that to help understanding why it makes sense, there's an alternative characterization of the minimization problem, which is given here. Ridge regression, let's start with that. All it's doing, in fact, is minimizing the mean squared error, or equivalently minimizing the residual sum of squares, but subject to a constraint. Subject to a constraint, and that constraint is really just the sum of the beta squares need to be smaller than some number s. Okay, this is some number s. Now this is alternative formulation of the ridge minimization problem. The initial one was the one where, okay, you have your residual sum of squares plus the ridge penalty that is lambda times the sum of the squares. But now here we're saying that you can show that this is the problem of minimizing the quantity under ridge as presented before is equivalent to minimizing the, the, the residual sum of squares, but under this restriction, under the restriction that the sum of the beta squares cannot exceed a certain quantity s. Now, this s is just depends on the lambda. Okay, this s just depends on the lambda. There's a specific lambda gives you a specific s in this alternative formulation. Now, likewise, I should say, for the lasso, all we're doing is we're minimizing the mean squared error, but under the constraint that we can never exceed the value s for all the sum of all the absolute values of the betas. I think this formulation makes it a little bit clear what happens. Basically, we're still minimizing the mean squared error, or alternatively the residual sum of squares, but now we have a budget to spend on the betas. We cannot let the betas be as big as we want. There's a certain budget of betas we can spend on all the coefficients. Now, we can spend it all on beta 1 if beta 1 really is the most meaningful. We can spend it all on beta 2 if beta 2 is really the most meaningful. We can spend it all on beta 3, or we can sprinkle this budget over all the betas, right? So in some sense, this is saying use your betas very wisely. Use your betas in the most efficient way because you only have so much beta in your beta budget. So that's why by constraining the betas, you're going to force your model to be as good as it can be, but without overfitting, without using lots and lots of predictors needlessly. Okay, so I hope this gives you a little bit more intuition about why it makes sense to regularize, to shrink the coefficients. Okay, here there's some technical details that I don't think I'm going to say anything about that. You can Google those concepts if you wish. Okay, and lastly, here there's we try to give you the intuition of something that we haven't really explained, which is why is the lasso forcing some coefficients to literally 0, and why the ridge doesn't? Now, frankly, it's a little complicated, but I think we can understand at least some intuition with this picture. So I'll try to explain it. Okay, so here we for the illustration we restrain our discussion to two coefficients. Okay, so imagine that you're minimizing the residual sum of squares for a linear model where you have two predictors. Okay, so you have two coefficients for the predictors, beta 1, beta 2. Now, so we use this alternative formulation, which means that beta 1 squared plus beta 2 squared needs to be smaller than some value s. Beta 1 squared plus beta 2 squared needs to be smaller than some value s. But this is exactly geometrically saying that the betas need to be within a circle. Well, yes, because the equation of a circle is if you have two coordinates on the Cartesian plane, x and y, well, the equation of the circle is x squared plus y squared equals a radius, right? Now, so visually, we're saying, okay, if imagine this circle as a radius of s, the only acceptable solutions, or the one that are allowed under the ridge penalty, are the betas inside the square. Okay, and the betas on the absolute outside of the square, or on the edge of the circle, would be the ones for which beta 1 squared plus beta 2 squared is exactly equal to s. So that's on the right plot, the ridge situation, the ridge penalty. Now on the left plot, you have a diamond, and that would correspond to a lasso penalty, because again, imagine you have two betas. So square root of beta 1 plus square root, not square root, sorry, the absolute value of beta 1 plus absolute value of beta 2 smaller than some value s. Geometrically, this means that beta 1 and beta 2 need to be between, well, inside this blue region, this diamond, where, by the way, the vertices are this vertex, this vertex, singular, I think, or vertex, is, beta 1 equals 0 and beta 2 equals s. This one is beta 1 equals s, beta 2 equals 0. This one is beta 1 equals 0, beta 2 equals minus s, and this one is beta 1 equals minus s, beta 2 equals 0. Okay, so this is, a diamond. Okay, within this diamond, for the values beta 1, beta 2 inside the diamond, you are respecting the condition that, well, this condition. Now, imagine, so in this picture, imagine the unrestricted solutions to the minimization of the residual sum of squares are this beta hat. Okay, so this dot represents the solution without restriction. So the solution under just regular least square is this beta hat. So the value of beta 1 would be here, and the value of beta 2 would be here. So you see, it's outside the diamond, or it's outside the circle. So it's not a valid solution under the penalties, under the Ridge and Lasso penalty. So you need to get away from the solution to find the best solution, or the closest best solution that is within the bounds of the penalties. So those red ellipses, they are contour lines, meaning, okay, if I go anywhere outside the optimal or the beta hat here, my RSS will start increase. So it's not going to be the best unconstrained solution, but all the values of beta 1, beta 2 that are on this ellipse, they have the same residual sum of square. Okay, all the values of the betas on the same ellipse, they have the same residual sum of squares. So if I go on an ellipse that is further outside, my residual sum of square gets worse, gets bigger, but again on the ellipse, they have all the same values. All the betas on the same ellipse have the same value for RSS. The point of this illustration is that, if you think about it, those ellipses, in the case of the Lasso penalty, so on the left dot, they can eventually hit the acceptable region for the solutions. They can hit it exactly on one of the axes. So you see, this is illustrated here. This ellipse hits the diamond exactly at the vertex beta 1 equals 0, beta 2 equals s. So then you get that the optimal solution under the Lasso penalty has a beta 1 of exactly 0. This is possible because the region is a diamond, and so it has a kind of a pointy, well, angle there. Because if you compare this to the square, the circle, there's no way an ellipse will ever hit the circle at a point where beta 1 is exactly 0, or beta 2 is exactly 0. It's just not gonna happen. Well, yeah, because, well, you have the illustration here. You're going to hit the circle at some kind of random point that, it would be an absolute coincidence of 1 in like a billion if the ellipse hit the circle at exactly beta 2 equals 0, beta 1 equals s, or the opposite. Okay, I don't know if that was helpful, but anyway, it's the illustration in the book, so I thought to present it here in case this helps. And I think I'm at the end of my slides. No, I forgot about this slide of comments about Ridge and Lasso. So let's review the few points here. Okay, I suppose it's actually a bit important. Okay, for both Ridge and Lasso, there is a cost to having the penalty, in the sense that as you have a bigger and bigger penalty, so you shrink the coefficient more and more to zero, you create bias in your parameter estimates for the beta. So you do create bias in the estimates for the betas. Well, yes, because I mean, imagine that the real data generating process is a linear regression model. Right? Just what generated the data is linear regression. Your standard estimates, no lasso and no ridge estimates of the betas, they are unbiased. They are unbiased. So if you alter the way they are derived, if you put the penalty, the lasso or ridge penalty, you are creating inducing some bias in your beta estimates. However, you're making them smaller, so the variances of the estimates will actually decrease. The variances of the estimates will actually decrease. And a way I think to conceptualize this is imagine the extreme case where the penalty is super large. Well, in that case, your estimates will be extremely biased, but you just estimate a straight line, right? You will just estimate that, well, yeah, that your model will just be y hat equals the mean of the y's, and that's a straight line. It's not very variable. It's not very variable at all. So yes, this is another example of a trade-off between bias and variance. As you increase the penalty, increase the lambda, the bias of your estimates increases, but their variances decreases. So overall, you can view finding the right lambda as the ones for which you've only introduced a little bit of bias in your beta estimates, but to the benefit of a substantial decrease in variance. So you're on the good side, or the good side of the trade-off between bias and variance. You pay a little bit of bias, but you receive a benefit of a largely reduced variance. Again, variance of the estimates of the betas. And for the rest, well, those are comments we've said many times. For ridge, all parameters remained in the model. Well, so some coefficients potentially very low. Okay, that's more difficult to interpret. Okay, remember the example where you had thousands of gene expressions. Hard to interpret. However, if all you care about is prediction, there's no problem with ridge. The fact that you have lots of coefficients, if you just want to predict the next y on on data you haven't you don't know what the y is, you just have the x's. For prediction, ridge is fine. For interpretation, it's hard to interpret if you have tons and tons of coefficients. So you might prefer lasso if you want parsimony, if you want to remove as many predictors in your model as you can. And they're both computationally pretty efficient. So unlike best subset selection where you need to fit hundreds or thousands or millions of models, here you basically just fit one model. Well, one model per lambda, right? But you just testing a couple hundreds lambda is fine, and then it's much more efficient than best subset. And I think that's it. Lastly, okay, there's a quote here. It's a quote here from a book, but I don't think I'm gonna insist too much. This is one person's opinion, so you can review it for yourself. But yeah, I don't think I'm gonna comment on this person's comments on those methods. So yes, again, pretty long video. I'll stop here. Thanks so much for having followed. And yeah, hope to see you in the next video. And yeah, I suppose I'll see you later. Bye for now.